All right, here's another video from 4.5 where we're dealing with proportions, specifically dealing with hypothesis testing when you have proportions. In the previous video, I gave a quick little 5-minute intro talking about some of the symbols that will come into play here. In this video, all I want to do is some examples. And as I talked about in the last video, these examples can either use the classical method of hypothesis testing or the p-value method of hypothesis testing. And in this video, I want to tackle the classical method. And then I'll come back and make one more for the p-value method, and then we will have learned everything we need to learn in this section. So classical method of hypothesis testing, HT for short, but not for means or with means, instead with proportions. So what would such a question look like? I need something that's a yes-no thing. So let's see, last example I think I used, do you have a dog or not? So fine. Suppose I know that, I don't know, 44% is what Google told me of Americans own a dog. So this is a population parameter here. I'm talking about all Americans. 44% of them own a dog. All right, so let's see. What kind of claim could I make? I'm a teacher. I know a lot of teachers. Doesn't seem like that many have a dog. I'm surprised. I suspect that teachers are less likely to own a dog. I don't know. I don't really think that. I'm just trying to make up some example. I couldn't find any data on what percentage of teachers own a dog. So what I did is I went out and I randomly select, I don't know, let's say 200 teachers, and find that, let's see, make the math work out nicely. Let's say 40% of them. And find that 40% of them own a dog. And so my question is, can I conclude? I need to state my level of certainty. So maybe with 80%. I don't know if we've done that one yet. 80% certainty that teachers are less likely to own a dog. So this is the type of question that I would ask you if we were doing hypothesis testing. And in this class, it'll always be a 4-step process. But what I've told you is prior to starting those 4 steps, it's not a bad idea to read through the problem and label all the different statistics and parameters that are given to you in the problem. Make your life a little bit easier. So I'm going to do that first. Suppose I know that 44% of Americans own a dog. So this is a population parameter here. All right, this isn't of a sample, it's of the population. And it's not a mean, it's a proportion. So maybe you're thinking the letter P. And that'd be good if you're thinking the letter P, but it's actually not the letter P. This is kind of the baseline population proportion. It's the thing that's a lot like mu naught was the first time we did this. So the symbol we'll use for it won't be a P, it'll be a P naught. And the reason why is we're going to want to save the symbol P for something else. And I'll tell you what that something else is in just a sec. I suspect the teachers are less likely to own a dog. I randomly select 200. This is my sample size. In the past, we used the letter N for this. We still do. 200 teachers, and find that 40% of them. So this is just referring to these 200 teachers. This is a sample proportion here. So this is P hat. That's equal to 40%. Can I conclude with 80% certainty? If I have 80% certainty, that tells me that alpha is 20%. Not a bad idea to make note of that. That teachers are less likely. If you're going to underline one phrase in here, less likely is a good one to underline. This is telling you your claim, your alternative hypothesis, tells you that you have a left-tailed test. You don't have to write this, but P is the population proportion of all teachers. So not of all Americans, but of all teachers that own a dog. So much like the last time we saw this, when there were 3 different notions of average, in this problem there's 3 different notions of the proportion. There's 2 population proportions, the overall baseline population proportion, and then this kind of hypothetical, never given, but you want a symbol for it, population proportion that your sample represents. And the sample are teachers, so the population proportion P would represent the proportion of all teachers that own a dog. And then the third one is P hat, our sample proportion that we have here. All right, you have all that information, you can start the actual process. In our class, it's always a 4-step process. First step would be to state the null and alternative hypotheses. Last time around, we used H with a little 0 in the subscript for the null hypothesis and H with a little 1 in the subscript, or it could be an A. For the alternative hypothesis, this was called H naught and this was called H1. We're still going to use those symbols. This still means my null hypothesis is. This still means my alternative hypothesis is. Last time around, these weren't that bad because they always compared together the same two things. They were mu and mu naught. Mu was just the symbol mu, and mu naught was always given to you in the problem. It's similar, except instead of mu and mu naught, it's P and P naught. Because P is the 4.5 version of mu, just like P hat is the 4.5 version of X bar. So I'm going to be comparing P and P naught, which is given to me in the problem to be 0.44 or 44%. You can write it as a decimal or a percentage, it doesn't matter. Last time around, my null hypothesis, I always put an equal sign here. You still do. This is the skeptical point of view. If I go claiming that teachers are less likely to own a dog and you're skeptical, you're saying, nah, they're just the same. It doesn't matter if you're a teacher or just a normal, I don't know if that's the right word to use, American here. The proportion of all teachers that own a dog is the same as the proportion of all Americans that own a dog. It doesn't matter at all. Your claim is nonsense. I am skeptical. Your claim is that, or my claim is that teachers are less likely. Because it says less likely, you want a less than sign here. Last time around, this could be less than, greater than, or does not equal. That's still all true. You read here, I'm not going to try to trick you. Look for keywords like less than, greater than, more than, different than, those kind of things. Because you put a less than sign here, this is a left-tailed test, although I don't need you to make note of that. That's our first step. Our second step used to be to state and justify the shape of the distribution, then tell me the center and the spread. And that's especially important because when you draw the picture here, you draw normalized values or you include normalized values. So the reader really needs some context in order for your picture to make sense. Shape used to be normal, it still is, or approximately normal, either way is fine. The criteria that we used to use was that n is greater than or equal to 30, but what we've seen with proportions is that that criteria doesn't work, and we have to memorize a new criteria. We've seen n times p hat times 1 minus p hat is greater than or equal to 10, and we've also seen that n times p times 1 minus p is greater than or equal to 10. Turns out we're not going to use either of those in this section. I think the short answer is shape, center, spread is going to be the same thing you've done in the previous two videos, except instead of using p's like we did 2 videos ago, or use p hats like we did in the more recent video, we're going to use p naught. So I'm going to copy essentially what I see here, except change all the p hats to p naughts. Take you through that a little bit more slowly down here. It's annoying to scroll through these. The shape will still be normal or approximately normal, and the reason why will be n times p naught times 1 minus p naught is greater than or equal to 10. The center used to be given by p, now it's given by p naught. That'll be given to you in the problem at 0.44. And the spread, we had a formula for it, and it was p times 1 minus p over n, the square root of that. But now we're changing all the p's to p naught, so it looks like this. So it's the square root of 0.44 times 1 minus that number, so 0.56, divided by n, which I believe was 200 in this problem, but I'll double check. Yeah, n was 200. I don't know that you really need to know this, but for anyone who's really nitpicky here, I want to make the point that when we last saw hypothesis testing, I told you that we were cheating a little bit here when we said the center was mu naught, and that really the center was mu, but we assume the null hypothesis is correct, in which case mu equals mu naught. So the number you put in here is mu naught, but technically the center is mu, but you don't need to worry about all that. You can just write mu naught in that number. That's what I told you the first time through this, and maybe you remember that, maybe you don't. Same thing's true the second time through this. Technically, the shape, center, and spread should use P in all of these formulas like we did when we were dealing with probabilities, the normal CDF section. But we assume the null hypothesis is true, in which case P equals P naught. So the number that you put into these formulas ends up being the P naught number. Technically, that's what's going on here. Most students leave 243 without even knowing that. They just remember that, oh, this is the hypothesis testing stuff. That's when I make all the P's the P naughts, because that's how you get the numbers. If you want to think about it that way, that's totally fine. Just trying to show you the little minor things in case anybody cares. Anyway, shape, center, spread, I give all that information so I can draw a picture. There's two different pictures that you can draw, but since we're doing the classical method of hypothesis testing, I want to draw for you the classical method picture. And let's see, I'll do it down here. Classical method picture used to include three things, it still does. We used to start with the classical method picture by figuring out what alpha was equal to. It's 20% in this case. And alpha was always the area of our rejection region. And we just had to figure out, is that rejection region on the left, the right, or on both sides? Still is. Alpha is still the area of your rejection region, and it's still either on the left, right, or both sides. In this case, it's on the left because it's a left-tailed test. So I want to start out by depicting alpha, 20% in this case. And then what my test will come down to is, yes or no, is my test statistic in this region? This region's called the rejection region, or some books call it a critical region. And the test statistic, which can come straight out of my calculator, I just got to figure out, is it in this region or not? And well, how are you going to figure out if it's the region or not? You have to know where the region starts. And so you always make note of where the region starts. Where the region starts is what's called the critical value. And the way you figure out your critical value is with the inverse norm function in your calculator. Same as it used to be. Second, then variables. Inverse norm is the third thing on this list. Tell it the area to the left. If I want to figure out this point, the area to the left is 20%. Center and spread, I'm putting in 0 and 1 because, again, I want normalized values down here. I want z-scores. I hit enter, and it spits out the number negative 0.842, I guess, if I round to 3 decimal places. Note that the center, you're putting a 0 here, even though you set up here the center was 0.44, because this 0 represents this 0.44. This is a z-score. It's saying we're 0 of these things above or below this guy. Whereas this is saying we're 8.42 of these things below because it's negative this guy. At any rate, there's your critical value, and there's alpha, 2 of the 3 things that I want you to show me in this picture. The third one is the test statistic. Test statistic comes straight out of your calculator just like it used to. However, it used to come from pressing stat and then going to tests and selecting z-test, the first thing on this list. It doesn't now. And the reason why is because your calculator recognizes that this is a very common question, and it builds a function called the one prop z-test specifically for these types of questions. Just like there exists a one prop z interval that we use when we're dealing with proportions and trying to come up with confidence intervals, there exists a one prop z test. And that's what we're going to use anytime we have anytime we're in this section doing hypothesis testing. If I select one prop z test, you'll see what it asks me for is almost what was given to me in the problem. If you go back to this problem, it's going to ask me for p naught. Oh, cool, I have that labeled 0.44. And then it's asking me for x and n. I know n, right? That was the 200, but I don't know x. Like, x must be this 40%. That's the only other number given to me. No, it's not. Remember that p hat is equal to x over n. X is the number of teachers that own a dog, not the proportion of teachers that own a dog. If p hat is x over n, then that tells you that x is n times p hat. So if I want to know what x is when they give me this 40%, I better be able to recognize that, yeah, that's telling me that p hat is 40%, but it's also telling me that x is 80. Because 80 out of 200 means 40%. Because when I take n 200 and I multiply it by 40%, I get 80 as my answer. You want to be able to see this number and recognize p hat and x are really both given to you. Sometimes, if the problem's being friendly, they'll just give you x right off the bat. That's fine. But if they give you p hat, make sure that you can come up with x. X is 80, n is 200. Now it asks me what my claim is. My claim is that p is less than 0.44. Instead of using the letter p, because they already use the letter p to represent the p value, which is not at all related to this p, annoyingly, they write out the word prop in your calculator here. Fine. The point is that my claim is that this p thing is less than this p naught value. So this p thing is less than the p naught value. Hit enter here. Remember that when you're doing this, you can either hit calculate or draw. Either way will give you all the information that you need. But what I told you is use draw for the p-value method because it draws the p-value picture. When you're doing the classical method, you might want to do calculate, although it really doesn't matter. This gives you your test statistic. And if you're doing the classical method, that's the only thing that you care about in this output. My test statistic, z, which is still what it represents, it's what it used to use and it's what it still uses to represent my test statistic, is negative 1.140. So you got to decide, is that in your rejection region? It is in my rejection region, right? If 0's here and negative 0.8's here, negative 1.1, oh, somewhere out here. Z equals negative 1 point, what did I say, 140? That's my test statistic. Then we make our conclusion. The nice thing about the conclusion is it's really similar to what it used to be. We used to say yes or no, is your test statistic in the rejection region? It is, because my test statistic falls in the rejection region. Make sure you can see that from the picture. Oh, and I think I told you that you don't have to do this, but I typically make note of the test statistic in my conclusion. So I would have said, because my test statistic, and then maybe Z equals negative 1.40, falls in the rejection region, there is sufficient evidence to reject the null hypothesis. I told you it's a three-step thing. I said, tell me why you're doing what you're doing, because the test statistic falls in the rejection region. What that means for the null hypothesis means you can reject the null hypothesis, and what that means in the context of this problem. So I conclude that teachers are less likely to own a dog. That is the classical method of hypothesis testing when you're dealing with proportions. Before I end this video, I want to make one change to this problem and just run it through real quick, probably take another 5 minutes or so. The idea is, in this example, I gave you a left-tailed test. I think you could use this to come up with what you do if it was a right-tailed test. But what I want to show you, because it looks a little bit different, is what if it were a two-tailed test? What if, instead of saying less likely down here, maybe I can rephrase this in such a way that instead of being a left-tailed test, it's a two-tailed test. So something like, can I conclude, let's see, that the proportion of all teachers who own a dog differs, not as greater than, not as less than, but differs from the proportion of all Americans that own a dog, I guess is implied. All right, what if we changed it to that? What would change? Good news, not very much. For step one, my null hypothesis would be identical. I'd still say P equals P naught, which is 0.44. However, my alternative hypothesis would now be not that P is less than P naught, but that P does not equal P naught. Because my claim here, maybe the word to underline would be the word differs. 2, shape, center, spread, that'd be the exact same. 3, your picture. It's going to look a little bit different. I'm going to draw my picture. It's still approximately normal because shape, center, spread is the same. My alpha, the area of my rejection region, is still 20%. But now that it's a two-tailed test, maybe I should have written that up here. That 20% has to show up on the right side and on the left side. Well, if the 20% is kind of dispersed in these two different groups, that means there's 10% on the left and 10% on the right. Here's 10%, here's 10%. So it's not a critical value that I'm looking for this time. It's two different critical values, but I can get them the same way. It's just inverse norm. Area below this point would be 0.1. Center and spread are 0 and 1 because I still want normalized values. Tells me that's negative 1.28. Note my center is still 0. So if this is 0 and this is negative 1.28, then this must be positive 1.28. You could get that by using inverse norm and saying the area to the left of that point is 0.9 and then 0 and 1 if you wanted to. Or you can just recognize that these are going to be opposites. And now you got your two different critical values. And now what you want to do is find your test statistic. And to find my test statistic, I still hit stat, go over to test. It's still one prop Z test, the fifth thing on this list. I give it this same P naught, same X, same N. The only thing that changes is that now my claim is the proportion does not equal P naught. Although you see that that doesn't even really matter because when I hit calculate, I get the exact same test statistic. If you're curious, the thing that changes is my P value. But the p-value only matters if I'm using the p-value method of hypothesis testing. So really all I'm looking for here is the test statistic, which is still this negative 1.40. And it looks like in this example, it's still in the rejection region. Z equals negative 1.40. So I'd say because my test statistic falls in the rejection region, that's the same. There is sufficient evidence to reject the null hypothesis, that's the same. So I conclude that teachers are differently likely. So I conclude that, and maybe I can pick up right here, say the proportion of teachers who own a dog differs. I don't know, maybe differs from the national average or something. I'm not super picky on the wording, as long as you have the right idea. So that's two versions of the classical method of hypothesis testing. I'll leave it up to you to figure out what you do if it was teachers are more likely to own a dog. But the short answer is you would just change this to a greater than sign. So it would be right-tailed, so your rejection region would be over on the right, so your critical value would be positive, and your test statistic, when you put all the numbers in your calculator, you'd probably end up getting a positive number, and you'd have to see if your test statistic were in the rejection region. But that's the classical method of hypothesis testing when you're dealing with proportions.